Okay, so this is the final exam for Psych 522. Let's go over the instructions. Okay, so there's a combination of some short answer and there's also some multiple choice in there as well. So the job is to circle the best choice for the multiple choice. And for short answer, answer in the space provided. Now the space provided, you're going to see you can make that space. I'm going to post the PDF version and the Word version, but feel free to use the Word version, create the space that you need, and then answer right underneath it. So make sure you answer on the document. The exam is take home, so you may use any sources that you wish, but it must be written alone. So be sure that you're not writing it with anybody and you're not communicating with anybody about it. It has to be written alone. So the final exam is due on or before Wednesday, November 25 at 5 p.m. And it's roughly half theory and half application. So we're not going to go through each question here, but just as a brief survey of what we're looking at. So here's number 1. We have A, B, C, D. Question on MANOVA, ANOVA. Some of the questions you're going to see are fairly general over some of the things we've learned. They may not specifically address a method, but to see if you've kind of assimilated what we've talked about. Number 2, okay, suppose in theory that the number of response variables in MANOVA were reduced to a single variable. So imagine that, we know MANOVA has many response variables. So imagine that we reduced it to a single variable. Well, then with a single factor in the MANOVA as well, what are some consequences of this? So this would make it a one-way ANOVA. Basically, it becomes a one-way ANOVA. Under this condition, for what value of SS within would the corresponding Wilks lambda equal 1? For what value of SS within would the corresponding value of Wilks lambda equal 0? Briefly explain why this makes sense given that Wilks is an inverse criterion. So the job here is to reduce it down from an ANOVA to an ANOVA and interpret Wilks lambda in the context of the ANOVA. Question on polynomial regression. Polynomial regression and also, very generally what we've talked about in the course, right? That's how the questions kind of bring some things together. It says polynomial, but there's other kind of things. The overall theme of the course is present in the question as well. So what does your colleague say? Oh, they did a polynomial regression that fits nearly perfectly. I am such a clever scientist, right? Okay, so without knowing your colleague's data at all and without asking them to tone it down a little bit, your best and most knowledgeable response of the following possibilities only should likely be, which one's the best response? Okay, which one's the best? So you're circling only one of them. So even if you're, circling E, well, that's one choice, but you're not circling like B and C or anything like that. And in all of these, remember, you're looking for the best option. Some of them may be pretty close, but put what you believe is the best option. 4, 5, question on ridge a little bit. For this one here, some of the choices are just 2 of the above or 3 of the above. So if those are one of the answers, it kind of makes it a little bit easier. But imagine if you can get credit for just saying 2 of the above. You have to filter through those things. Support vector machines, you'll have to do a little bit of research on that. That's in James. And just to see what that procedure is about, okay, and whether it fits into this answer in terms of combining which techniques are possible. MANOVA, ANOVA, and then we get into principal components, factor analysis. Make sure you read the questions very, very carefully. Remember, in these multiple choice, there could be some slight distinctions you have to make. Right? So don't feel free to take your time to kind of look at it and maybe narrow it down to 2 or 3 choices and then try to split hairs between the choices. Question on supervised versus unsupervised. Now remember, some of these things we've talked about, and some of them you may have to just think about it, right? So when we think of it like a t-test, well, you're not really going to see t-test. identified very much as supervised or unsupervised, but if you had to put them into one category or another, which one would it be? So some of these questions are asking you to reason through it a little bit, give your best answer based on what you've learned. This question here, what's the best way of characterizing this thing called statistical learning? So remember at the beginning of the course, we wanted to answer that question, what is learning? What is machine learning? What are these ideas about? Well, the title of the book is called Learning, right? It's called Statistical Learning. So which one of these two choices best sums up the idea of what statistical learning actually is? And one thing that I hope we've learned from the course is to be able to identify what this term means. So when you hear terms like machine learning and statistical learning, they're not always going to be one of these things, but it's very much encapsulated into one of these ideas. So remember, you're trying to unify this so you have a real understanding of what statistical methods do and what they don't do. And if you can identify what this learning phrase means, it goes a long way to kind of joining things together. Some application, there's some stuff on MANOVA, here's some stuff on PCA. So in this one, you want to change the first loading from this value, it's this loading right here. Change it to 0 and adjust it in the plot. So, right in the plot, maybe you have to do this, I don't know, but you're adjusting it in the plot to show that that change in loading corresponds to the change that you're producing in the plot. There's a scree plot, some question on the scree plot. There's a factor analysis. So we've got some loadings in factor analysis and which one of these are true. And we have a factor analysis here. So we have different tests. So we have a whole bunch of observed variables here. Right? These are observed variables. And these are the number of factors. So we've got factor 1, factor 2, et cetera, up to factor 5. And then here we got this unique term. So the question is, you have to demonstrate the computation of the unique number of 0.453, which is right here. How is this computed? And what does that number mean? Okay. Based on our lookup factor analysis, you should be able to do that. You might have to do a little digging to refresh on what that number is, but identify what it means and show the computation. So when you're doing the exam, you can leave some space here and put the computation down here. Again, for questions like this, you're not writing like big paragraphs. You're demonstrating the computation and then you're talking a little bit about what it means. If you write too much information, remember, you can get a point deducted for saying something that's wrong. So you don't want to, the comment on what it means, you don't want to write like a whole page and hope something sticks. Because if you say something wrong, then I'm going to take off, you can lose the full point. So make sure what you say is accurate information. What is the communality estimate for test 25? Demonstrate its computation. So there's test 25. And what is the communality estimate for that particular test? Demonstrate the computation for it. Show how it's computed in here. There's another principal components analysis. The variance for PC1 is equal to 2.649. What's another name for this variance? What's another name for this? Now there, I'm not looking for you to identify what the component is. I'm just saying, if you had to replace this with another name, what would it be? What would you say, the second part, what would you say component 1 is made up of primarily? That's where you're looking at the loadings. Demonstrate the orthogonality condition for PC1, PC2. Now you can do that by hand if you like, or you can do it in R, but that's not like an R question. But if you want to do it in R just to simplify the computations, you can do it. But for the simplifying the computations, you're going to have to take this information and construct, some vectors, right? So you might want to construct a vector here, based on this information to demonstrate the orthogonality condition. Or again, you can do it by hand, but it may be more convenient to just set that up in R. But nowhere in there should you have any problems doing it in R, because you're not having to download any packages or anything like that. So in that way, the exam is not contingent on whether R is behaving properly and stuff like that. Demonstrate that PC5 has been normalized. Identify that that has been normalized. Suppose instead the variance for PC1 equal to 2.649 were equal to 1.0. So imagine if that variance was equal to 1.0, while all other eigenvalues remain the same. So don't change a thing in the rest of it. Why would the PCA output be suspect in this case? So if your PCA came out to be this is equal to 1.0, that's what you see for output, why would that be a suspect PCA? Take this data, perform a MANOVA on it, and again, you can do that in R. You could also do it in SPSS if you want to do the MANOVA. Probably easiest to do it in R. There's your Y1, Y2. There's your independent variable. This has got 3 levels, 1, 2, and 3. Perform the MANOVA on the above and demonstrate that Pillai's trace can be written as a function of eigenvalues. These are the eigenvalues, and these are the number of dimensions that you're extracting. Now, be careful about this question. This question is going to take some thought because the question asks you to do a MANOVA. Okay, it asks you to do a MANOVA. But when you look at this, you may have to do some side work. You may have to do some extra work to get the eigenvalues. Okay, there's a hint for that one. You may have to do some extra work to do these. What that extra work is, you can do anything you want to get it, but you may have trouble getting the eigenvalues from doing the MANOVA. Then justify why, if there are only 2 groups on the independent variable, this Pillai's trace would reduce to this number. So by justify, you can show it in your computation, right? You can say, look, here's the output that I obtained. Look, this is equal to this. You show it with the numbers and then put a brief comment as to why that makes some sense, right? So you're using the numbers by justify. We just mean use the numbers from your output to kind of show why that's true, and then maybe put a brief comment as to why this makes sense that this is true. Right? Why does this make sense? So you don't want only to put the numbers. You want to say this makes sense because, etc. Okay. Demonstrate for the above ANOVA that the Lawley-Hotelling's trace can be written as a sum of eigenvalues. Again, it might require some side work, something else to get these based on what you've learned in the course. And given this fact, for any given MANOVA, it must be less than Pillai's trace. Why must this number be less than Pillai's trace? An eigenvalue in PCA, one more note here. When we're saying it must be less than Pillai's trace, well, you're looking at the computation, but you're answering the question as to why it must be less, right? You're not just saying that it's less, right? You're not saying, well, because the number 2 is less than the number 3. You're commenting on why it must be less, why it makes sense that it's less than Pillai's trace. So again, a little bit of using what you're finding from your output. The output is guiding you to understand and explain what the question is asking. That's the gist of this. Okay. An eigenvalue in PCA is the same eigenvalue obtained in discriminant analysis. Do you agree? Why or why not? Provide a technical justification. Now, by the technical justification, we don't necessarily mean just throw down a whole bunch of formulas and hope something sticks. We mean think about the problem here, that the PCA and how it associates with eigenvalues in relation to discriminant analysis. How are eigenvalues defined in discrim? How are eigenvalues defined in PCA? Are they the same? Right? Are they the same eigenvalue? And by that, we don't mean the same number. We don't mean, yeah, this is a 2 and this is a 2. We mean, is it the same thing? Is it based on the same thing? Provide the technical justification. So your technical justification would be something like this. The eigenvalue in PCA is based on, the eigenvalue in discrim is based on, and provide that technical justification. May require a little bit of digging. You might want to look at your sources a little bit to see what's going on here. Is an eigenvalue an eigenvalue, or is it based on different things? Justify on technical grounds why the definition of a cluster in cluster analysis is arbitrary. Now there's a whole 5 points for that. Think about that question. That may require a little bit of thinking as to what we've talked about in lecture, but how is it arbitrary? And define it on technical grounds. Now by technical grounds, we mean, kind of like that mathematical machinery. What is it about cluster analysis that can make the definition of a cluster arbitrary? If you say something like, well, because we don't know what a cluster is, well, that's not a technical justification. You want to get into what the cluster analysis actually does to justify. You say, you know what, they can be considered arbitrary because this is what cluster analysis does, which is what makes it arbitrary. If you say it's arbitrary, and let me just tell you what cluster analysis does, you're not connecting the two things, right? It's arbitrary because of what cluster analysis does. Now, what is it about what cluster analysis does that makes the definition of a cluster arbitrary? Okay, so just to clarify there, you don't want to just unpack what cluster analysis does. You want to associate it to it being arbitrary. If you can't associate it to being arbitrary, then all you've done is unpack the procedure, and that's not going to get you the points. You have to identify what makes it arbitrary. On what grounds could cluster analysis be considered arbitrary? And the only way to do that is to look at it in technical grounds. But again, just as the caveat, you don't just want to unpack a whole bunch of math and just say there's a whole bunch of math connected to arbitrary. In number 10, why is it true that a dendrogram alone will not provide a conclusive verdict regarding the number of clusters that may exist in the set of data? What is it about the dendrogram that doesn't provide the ultimate verdict? Okay, so that's it. There's a total of 45 points. And when you're looking at it, I mean, if you're not sure of a question, do the best you can with it, right? Especially for some of those multiple choice where it could be between one or the other. Some of the short answer, you can do the best you can with it, but again, be careful not to put down information that's false, because that will, points will be removed for that. So, suppose you're looking at this question and you're wondering, I have no idea how to answer this question or stuff like that. If you put down a false claim about cluster analysis or something like that, points will be removed for that. So whatever you put down, you want to put down stuff that you're pretty sure is getting at the heart of it. So narrow down what you're going to put down. But it doesn't mean you can't, if you're not completely sure, well, you're putting down your best argument. That's what I'm getting at. Put down your best argument, but make sure it's your best. Don't just put down a whole bunch of stuff and hopefully you get some points from there. Okay. Okay. So that's it for the final exam, and it is due on travel day. So it's due, the latest is due on travel day and at 5 o'clock. So best of luck to you.